Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 30. In this lecture, we'll discuss conservation of energy. This topic is covered in Chapter 8 of our textbook by Surway and Jewett. So in this lecture, we want to discuss perhaps the most important concept in this entire course, namely conservation of energy. We've been talking about energy for a few lectures now. We've talked about kinetic energy. We've talked about different types of potential energy. We have mentioned how the whole concept of energy rests on the idea of work. We've talked about the work done by conservative forces and non-conservative forces. And now we want to tie all of that together under the concept of conservation of energy. Let's review some of these concepts. Recall the work energy theorem. The work energy theorem tells us that the net work done on an object is equal to the change in the kinetic energy of that object. Recall that kinetic energy is 1/2 mv squared, so it depends on the speed or velocity of the object, and therefore kinetic energy is sometimes referred to as energy of motion. And the work energy theorem tells us that the net work is equal to the change in that kinetic energy. Recall that this equation is valid for all forces, whether they are conservative or non-conservative. Of course, in general, you might have multiple forces working or acting on an object. You might have 8 different forces acting on a box, and some of those forces will be conservative forces, like gravity or the spring force, and then some of them might be non-conservative forces, like drag and friction. And therefore, when we talk about the net work, we have to talk about the sum of all of those forces, which means we can express W net as the sum of the work done by conservative forces and the work done by non-conservative forces. The important idea here is that you cannot use the work energy theorem for individual work. It must be the net work on the object. We've also learned that for conservative forces, work can be expressed as the negative of the change in potential energy. There is no potential energy for non-conservative forces, but for conservative ones, we can take advantage of this equation. We now want to combine these 3 equations. Specifically, I want to replace W net here with delta K. So I'm going to take delta K and substitute it in this equation. And I also want to replace W conservative with minus delta U. So now I'm going to take minus delta U and substitute it in for the work done by conservative forces. When I do that, I get the following equation: delta K plus delta U is equal to work done by non-conservative forces. And this equation is probably the most important equation of this semester. It is often described as the conservation of energy equation, although to understand what it has to do with conservation, we have to start using this equation a few times. The message here is that according to this equation, any change in kinetic energy or change in potential energy must be accompanied by work that is performed by non-conservative forces. So you will see and use the conservation of energy equation in many different contexts. This equation is incredibly common, and therefore you'll see it written in many different forms. So the form that we just introduced it in was as follows: delta K plus delta U is equal to the work done by non-conservative forces. But often you'll see the same equation written as delta E is equal to work done by non-conservative forces. This E here refers to the mechanical energy of the system, and the mechanical energy of the system is simply the sum of its kinetic energy and potential energy. A little more precisely, when you see the term mechanical energy, you just simply need to think of the sum of K and U. The same equation is also sometimes written as K final plus U final is equal to K initial plus U initial plus the work done by non-conservative. That should make sense because, again, this delta K over here is a change in kinetic energy. So this is really K final minus K initial. And similarly, the delta U is U final minus U initial. If you bring all of the initials to the right side of the equation, you will see that the final kinetic energy plus the final potential energy must be equal to the initial kinetic energy plus the initial potential energy, plus any work that is done by the non-conservative forces like friction or drag. In many of the examples or problems that we'll encounter, non-conservative forces will be absent. So we'll often deal with problems where we want to ignore drag because it's negligible, or we'll deal with problems where there is no friction, for example, because the object is sliding on ice or on a very smooth surface. So we can say that there is an absence of non-conservative forces. If the non-conservative forces are absent, then they are not doing any work. In that case, we can say W non-con is equal to 0. When that happens, the three equations that we listed up here simplify a little bit. This first equation simply becomes delta K plus delta U is equal to 0. This second form of the same equation just becomes delta E is equal to 0, and this last form simply just becomes K final plus U final is equal to K initial plus U initial. Notice you can use these three equations only when you've been explicitly told that there is no friction or drag, when you know that the non-conservative forces are absent or somehow eliminated. When you write the conservation of energy equation in these forms, you can see better why it's called the conservation of energy. In this context, to conserve means to keep constant. When something remains constant in value, we can say that it is conserved. And these equations are essentially telling us that the kinetic energy plus the potential energy, that total quantity, remains constant, therefore it is conserved. For example, in this last form, you can see that the final mechanical energy must equal to the initial mechanical energy, and therefore we would say mechanical energy is conserved. The conservation of energy equation can be used to solve many interesting problems. However, applying the equation to actual problems can be a little bit tricky. In that respect, it's helpful to recognize that non-conservative work that's done by friction and drag and other non-conservative forces, can be thought of as a type of energy transfer into or out of the system. So usually you begin problems by considering a system like a falling apple or a box sliding across the floor. Non-conservative forces will be performing work on that system, and what they will be doing is transferring energy either into or out of the system. So it helps if you have the following picture in mind. You can think of your system, whether it's the apple or the block or the spring, as having some mechanical energy. That mechanical energy has two components, kinetic energy and potential energy. If there are no non-conservative forces, if drag and friction are absent, then the total mechanical energy remains constant. Energy can be transferred between kinetic and potential energy back and forth, but everything inside the dashed lines remains constant. On the other hand, if you have non-conservative forces like friction and drag, then you'll end up with a transfer of energy into or out of the system. In general, drag and friction will perform negative work, therefore they represent a transfer of energy out of the system. As you will learn in other physics classes, we could also heat the system up, we could also use electromagnetic fields to change the energy of the system. In that case, we would have a transfer of energy into the system. Regardless of what the non-conservative forces are, it's useful to have this picture in mind because it helps you manage or account for the input and output of energy that the system is experiencing. This picture is a lot like how you might manage your own finances. For example, you might have a bank account with some amount of money in it. That money might be split between your checking account and your savings account. And then, of course, you have certain incomes and expenditures. So the rent and the food might be expenditures, and they represent sort of an output of money from your bank account. And then if you're working, your wages and your tips represent an input into your bank account. And so essentially the conservation of energy equation can be thought of as an accounting or a balancing of the number of joules that a system possesses. This analogy between mechanical energy and your bank is not very precise, but it's a nice picture to have because it will guide your thinking as you solve actual problems. Let's do a practice problem involving conservation of energy. A projectile with mass 1.5 kilograms is fired from a height of 12 meters with initial speed 20 meters per second at an angle of 30 degrees from the horizontal. Ignoring air resistance, what is the speed of the projectile when it has reached a height of 16 meters? Now, hopefully you recognize this as a classic projectile motion problem. We studied this kind of a problem back in chapter 4, and there we learned to use the two-dimensional kinematic equations to answer problems like this. There we learned how to figure out the range or the time of flight or the maximum height of this projectile. It turns out many of those problems can also be solved using the conservation of energy equation, which we just learned. So our goal here is to actually solve the same problem using a different strategy now. If we want to talk about conservation of energy, we first need to think about non-conservative forces, and we need to calculate the amount of work that they do. In this particular problem, we're ignoring air resistance, so we can say that air resistance is equal to 0. If the force of drag or air resistance is equal to 0, then the work done by this non-conservative force is 0. So that simplifies the problem quite a bit. And of course, there is no friction because this thing is not sliding across the floor, it's flying through air. So that simplifies the problem a little bit for us. Immediately we know that we can use conservation of energy in this form. Delta K plus delta U is equal to 0. Or if you want, you can use this equation, delta E mechanical is equal to 0. Or you can also use this form of the same equation, K final plus U final is equal to K initial plus U initial. In most practical problems, this last form is probably the best form to use, although these three equations are mathematically equivalent. To use any of these, you need to know something about the energy, specifically the kinetic energy and the potential energy of the projectile at different points, initially and finally. The initial position refers to the position of the projectile on the hill, and its final location will be at a height of 16 meters. Incidentally, notice that we don't exactly know whether this height of 16 meters corresponds to the maximum or not. As it turns out, the maximum height of this projectile is actually 17.93 meters, but that information is not provided in the problem. To proceed, we calculate each of the energies. We can calculate that the initial kinetic energy is 300 joules. I've calculated this number by using the formula 1/2 mv squared. M is 1.5, and v, of course, is the initial speed of 20. Plug that into your calculator, and you will see that the initial kinetic energy is 300. What's the initial gravitational potential energy? For that, we use the formula mgy. And of course, I'm going to use 12 meters for y, the initial height of the projectile. If you plug all that into your calculator, you will see that the initial gravitational potential energy is 176.4 joules. Now we want to know the speed of the projectile when it's at 16 meters. At that point, we don't really know what the velocity is. That's the thing we're trying to solve for. And therefore, we cannot really figure out the final kinetic energy. The best we can do is just simply say that the final kinetic energy is 1/2 m v final squared. We can figure out the final gravitational potential energy. Again, gravitational potential energy is given by the formula mgy. The y now, the final height, is 16 meters, so you can plug that in. and find that the final gravitational potential energy is 235.2 joules. Now we know, thanks to conservation of energy, that K initial plus U initial must equal to K final plus U final. In other words, delta K plus delta U is equal to 0. If I were to write that out a little more explicitly, I would have this type of an equation. You can now plug in all of the numbers. The only thing you don't know is K final, or more precisely V final. And then you can do a little bit of algebra to find what V final is. Turns out the final velocity is 17.9 meters per second. I encourage you to solve this problem on your own using the kinematic equations. You should get exactly the same answer. However, when you use the kinematic equations, you'll see that there's a lot more algebra involved. Here we found the answer with very little algebra. We did not need any trigonometry. We did not need to use the quadratic formula. With relatively simple algebra and the use of conservation of energy, we found the speed at a height of 16 meters. Let's do another practice problem involving conservation of energy. This practice problem is quite similar to the practice problem we just solved. However, this time we're going to include air resistance in our calculations. A projectile with a mass of 6 kilograms is fired from a height of 80 meters with initial speed 15 meters per second at an angle of 35 degrees from the horizontal. When the projectile has reached a height of 70 meters, its speed is 18 meters per second. Calculate the work done by air resistance. Notice here we're definitely not ignoring air resistance. We're going to assume that air resistance is present, and here we want to figure out what its effect is. We want to know how much influence air resistance has. More precisely, we want to calculate the work done by air resistance. We are told that at a height of 70 meters, its speed is 18 meters per second. Just for your information, without air resistance, the projectile's speed at a height of 70 meters would have been 20.53 meters per second. Don't worry about how I did this calculation. My intent here is just to show you that air resistance is having a significant effect here. It's clearly slowing down the projectile quite a bit, from roughly 20.5 meters per second to roughly 18 meters per second. But of course, we want to make all of this precise. We want to know exactly what the work is that air resistance performs on this projectile. Once again, we want to use conservation of energy. Once again, we figure out the initial kinetic energy and the initial potential energy. To figure out kinetic energy, I'm using 1/2 mv squared. For potential energy, we're talking about gravitational potential energy here, not spring potential energy. For that, I'm going to use mgy. Plug in the numbers and you will find the following values. Now we proceed to the final situation. We're now at a height of 70 meters. The speed is given to us this time, so we can actually calculate the final kinetic energy. Again, 1/2 mv squared, but this time you use the final speed. That gives us 972 joules. And of course, we're interested in the potential energy as well. We need the final height of 70 meters. Plug all of that into your equations, and you will find that the final potential energy is 4,116 joules. Now, recall that the conservation of energy equation tells you that the work done by the non-conservative forces is equal to delta K plus delta U. In this case, the only non-conservative force we worry about is air resistance or drag. We can figure out delta K. Delta K is simply K final minus K initial. We can figure out delta U. That's just U final minus U initial. When we plug all that in, we find that the work performed by air resistance is minus 291 joules. Chapters 7 and 8 of our textbook are really about work and energy and all the relationships between them. In these two chapters, we've covered a lot of equations and a lot of important concepts, so here I want to review all of them in one place. The first concept that we were introduced to was work as the influence of forces, and we found that work is the integral of F dot ds. Here you have to know what ds is, you have to know what the dot product is, and you have to be able to perform integration. When the force is constant, you don't need to bother with all of that. You can just use this equation here. In fact, this was the way we initially introduced work, as simply the product of force and distance. But of course, don't forget the cosine of the angle between force and distance. We talked about the work-energy theorem, which connected work to kinetic energy. And then we found that for conservative forces, we can connect work to potential energy. We like to connect everything to everything, and in chapter 5, we'd learn about forces. So here we can connect forces to potential energy. Forces, of course, are vectors, so they have an x and a y component. Potential energy is a scalar, it's just a number. But if you take the derivative of that scalar function with respect to one variable, you'll get the x component of force. If you take the derivative with respect to another variable, you'll get the y component of force. Putting everything on the left side together, we came up with the conservation of energy equation. Delta K plus delta U is equal to W non-conservative. Often we will set W non-conservative equal to 0 because we are told that there is no friction or drag, in which case this equation simplifies a little bit. To use this equation, you need to be able to calculate the change in kinetic energy and the change in potential energy. The change in kinetic energy is simply 1/2 the change in V squared. So we have 1/2 m V final squared minus V initial squared. Note that the squares are inside the parentheses, not on the outside. To calculate delta U, you need to know what kind of a potential energy we're talking about. If it's gravitational potential energy, then delta U is going to be mg delta y. If it's spring potential energy, then delta U is going to be 1/2 k delta x squared. If you happen to have a problem in which there's both gravity and a spring, then this delta U needs to include both changes in potential energy. So you'll have to calculate delta U sub g and delta U sub s, add them together, and then together that gives you the delta U that goes into the conservation of energy equation. Let's finish this lecture with a rather lengthy practice problem. A block of mass 10 kilograms initially at rest slides a distance of 4 meters down a frictionless incline forming an angle of 30 degrees with a horizontal. Calculate the kinetic energy, gravitational potential energy, and spring potential energy of the block at the top of the incline. So this is going to be a multi-part problem, and for the beginning part, what we have is an inclined surface and a block that is initially at the top, but it begins to slide and it reaches the bottom. To begin with, we just want to know what the energy is while it's at the top of the incline. We're told that it is initially at rest, which immediately tells us that the velocity must be 0. So if you've seen a problem like this on your homework, or if you see it on an exam, immediately you should say something like V initial is equal to 0. And of course, if V initial is equal to 0, then K initial must be equal to 0 because K is 1/2 mv squared. At the top of the incline, there is no spring, so immediately you should think that the spring force is also equal to 0. If there is no spring, there cannot be any spring potential energy stored in the mass spring system. And the only non-zero energy that we need to worry about is Ug. Notice we're talking about the gravitational potential energy, not the change. And of course, gravitational potential energy is given by this formula, mgy. We do need to know what the initial height of the block is. Remember, we're talking about an inclined surface like so. We're given this angle over here as 30 degrees. And we're told that from the top to the bottom of this incline, the distance is 4 meters. What we're really interested in is in the height of this inclined plane, and we can calculate that using a little bit of geometry. We can find that this height must be equal to 4 sine of 30. So we can calculate the gravitational potential energy by multiplying m with g with 4 sine 30. The end result of all that is this. The kinetic energy at the very top is 0. The gravitational potential energy is mass times gravitational acceleration times the height, which is 196 joules. And the spring potential energy, of course, is 0 because there is no spring there. We will introduce a spring into this problem soon, but at this point, the spring potential energy is 0. Part B asks you to calculate the same energies at the bottom of the incline. So now the object has had a chance to slide to the bottom of the incline. By the time it reaches the bottom, it has sped up. Gravity has been pulling on it. So the kinetic energy is no longer 0. The potential energy is going to be 0 because by the time we reach the bottom of the incline, the height is 0. And of course, there's still no spring in this problem, so the spring potential energy is going to be 0. Calculating the kinetic energy can be difficult. The difficult way to calculate the kinetic energy is to say that weight is pulling the block down. We don't worry about friction because this is a frictionless incline. Of course, weight acts in both x and y direction. Here we're using a rotated xy coordinate system. In the parallel direction, weight is mg sine theta. Of course, that's going to be equal to mass times acceleration, thanks to Newton's second law of motion. So the acceleration of the block in the parallel direction, which we're calling the x direction, is going to be g sine 30, or 9.8 times sine of 30, which ends up being 4.9 meters per second squared. Notice that this block is not in free fall, it is sliding on an inclined surface, so it makes sense that its acceleration is less than 9.8. Once we know the acceleration, we can use our kinematic equations to find the final velocity, and we find that the final velocity at the bottom of the incline is 6.261 meters per second. Now that we have the velocity at the bottom of the incline, we can calculate kinetic energy. Kinetic energy is 1/2 mv squared, and when we plug in those numbers, we find that the kinetic energy is 196 joules. The gravitational potential energy is 0 because the y is 0, and the spring potential energy is 0 because there's no spring. This was the hard way to calculate this problem. Of course, if you understand what conservation of energy means, then you understand that the sum of these three energies at the top must equal to the sum of the three energies at the bottom. So without doing any of these complicated calculations, you could have just told me that the kinetic energy at the bottom of the incline is 196 joules. However, I encourage you to do this problem both the easy way and the hard way, just so that you have a little bit of extra practice. Let's continue that practice problem. Part C says when the block reaches the bottom, it slides a distance of 13.3 meters across a horizontal surface with a coefficient of friction of 0.1. Calculate the work done on the block by friction. So we had a block, it slides down an inclined surface, and now it's reached the bottom, and now it's just sliding across the floor, let's say. It slides a distance of 13.3 meters, but there is friction on the floor. The coefficient of friction is given to us. Here we want to calculate the work done by friction. Remember that work is the integral of force and distance. Here everything is moving in the x direction, so we can just replace distance with dx. And of course we need to know what the x component of force friction is. Remember that the magnitude of friction is mu mg, at least on a horizontal floor, and its x component is going to take a minus sign in front. So the x component of the force of friction is pointing to the left, so we say minus mu mg. If you want, you can also write this integral as mu mg times cosine of 180. The cosine of 180 is going to give you this minus sign in front. The mu, the m, and the g are constant. You can bring those out. The integral of dx is simply x. And then, of course, you have to plug in the limits of integration. We're going to say that the bottom of the incline is x equals 0. It's going to slide a distance of 13.3 meters. We're calling that d2. So we can say that the work done by friction is minus mu mg d2. The minus sign is telling us that the force of friction is opposing the velocity of the block, so it's having a negative influence. How much of a negative influence? Well, friction ends up doing minus 130.6 joules of work. The bar over the 6 simply indicates that this is a repeating 6, so the exact answer is minus 130.6666666, or just 130 and 2/3. Part D is a little more complicated. After sliding across the horizontal surface, the block reaches a spring with constant 150 newtons per meter. The block compresses the spring by a distance of 0.93 meters before coming to rest. Calculate the 3 energies of the block when it comes to rest. So just to review, the block slides down an inclined surface, it encounters some friction, it slides across the frictiony floor, and then it finally comes to a spring. It hits the spring, it squeezes or compresses the spring, and after compressing the spring by this distance, 0.93, it finally comes to rest. At that moment in time, calculate K and the gravitational potential energy and the spring potential energy. Well, if the block comes to rest, then its kinetic energy must be 0. The block is on a horizontal surface, its height is 0, so the gravitational potential energy should be 0. However, it has now compressed a spring. The mass spring system now has some stored energy. We call that spring potential energy. And the formula for spring potential energy is 1/2 kx squared. So we have 1/2 the spring constant of 150, and x refers to the compression of the spring. You can call it minus 0.93 if you want, but we're going to be squaring it, so it doesn't really matter. You put all that together and you find that the spring potential energy at the bottom is 65.3 joules. This is maybe the hard way to answer this question, but you could have also recognized that we have conservation of energy. At the very top of the incline, the block had 196 joules of energy. When it slided across the floor, it lost 130.6 joules of energy. Remember, we think of friction as basically an expenditure. It's taking energy or transferring energy out of the system. And if we take our initial 196 joules, we transfer out 130 joules, what we're left with is 65.3 joules. So again, you could have just figured out this final answer without this formula 1/2 kx squared. It's a nice check on your calculations, but notice that conservation of energy makes all of these steps much easier. And that's the end of this lecture. Thank you for your attention.